My name is Doug Rohrer. I am a polyglot developer who happened to end up doing some Elixir work a little while ago. I'm going to kind of tell you the story of how I got to do some Elixir work, why we ended up choosing Elixir, and where we came from, and then some of the interesting stumbling blocks we ran into so you don't run into them as well. This is a little bit about me. One of the big things throughout my career is I have been involved in analyzing and mitigating performance issues in systems, be it .NET, Ruby, Elixir, Erlang, sorts of things. So this kind of problem is something that I've done a lot of over the course of my life in a lot of different languages, and I learn something new every time I do it, so it's a lot of fun. So the problem that we ran into, the client is a home automation company that does a lot of different things, including connected thermostats as one of their devices. And no, it's not Nest, it's somebody else. But same basic concept, right? You've got a thermostat in the home connected via Wi-Fi. I want to be able to turn up the temperature because I'm coming home early, so I pull out my iPhone and crank up the temperature a couple degrees, and by the time I get home, my home is nice and comfortable. They had a very high-end product of which they had about 3,000 or 4,000 on the market that were actually installed in people's homes. And they wanted to expand that to a broader audience, so they built a less expensive, slightly less high-end system that was going to be manufactured in the 100 to 200,000 unit range within the next year. We had an existing system that ran in Ruby that handled the 3,000 to 4,000 thermostats fairly well, with a couple of exceptions, the big one being anytime they had any sort of networking issue at their hosting provider, when the thermostats came back, they all came back at the same time, and the system really couldn't handle all of those new incoming connections at once. So the question was, can the existing Ruby system scale to this orders of magnitude larger number of devices that we're planning on selling in the next year? If so, how do we make it do that? If not, what do we do? What are our options? So again, we had an existing system, so we built a performance testing tool excuse me, that could simulate load for a large number of devices, look at a potential solution, starting with the existing one, run the test, see how close we could get to what we projected our load numbers to be, both in terms of these kinds of new connections coming in all at once, sorts of spikes, and then steady state load. Try and figure out, okay, it's not working, where isn't it working? Why isn't it working? And try and fix those things. And then when we got to a point where there wasn't an obvious problem that we could easily fix, abandon that solution, move on to some other proof of concept to see if we could get to a final answer that would actually work for us. So we started out with the existing solution, which was based on Ruby and an event loop model called Event Machine, which uses, I believe, the same code that things like Node use, libuv. It's a typical event loop. That already existed. It was up and running. We had some really interesting problems when we tried to scale that up. The first of which was it just could never handle the number of new connections that we needed it to. There may be some lower level tweaks now that I know a little bit more about how TCP/IP and acceptor loops and those kinds of things work that we could have done. But at the end of the day, the biggest problem for us was, as an evented looping system, if you don't yield back to the event loop often enough, you end up stuck in places where certain things are totally consuming the processor and totally consuming the system. And in our case, what would happen is we would pull all of the messages that we had off of a RabbitMQ queue before we could respond to any of them. And we fixed a bunch of bugs in the AMQP gem, which is what Ruby uses to talk to RabbitMQ, but couldn't find the right place to put in a please yield back to the reactor loop in order to make that work and work reliably. There's another system in Ruby that's also known for handling these kind of large concurrent systems called celluloid.io. It uses an actor model or agents to handle connections. The programming model is a lot easier to understand than this event loop style system. But it ended up, the only way we could get the system to accept a large enough number of connections per minute was to use JRuby. And at that point, the system that we were looking at, maybe a single machine hosting 40 or 50,000 simultaneous connections, was using 40 gigabytes of RAM. Again, at some point, there may be some things that we could have done to lower that, but I don't think it was an order of magnitude sort of fix. So we looked at that and said, 40 gigs of RAM for a bunch of active connections is really not going to be feasible for this system. So our next thought was, we should look at Erlang. As many of you probably know, Erlang was pretty much designed for these kinds of problems. This is what Erlang is really, really good at. So concurrency is a lot easier to do and is more supported by the runtime in Erlang, especially than a Ruby-based system or pure MRI Ruby. OTP forces you into doing things like using the actor model in order to implement your system. So if you stick with kind of known patterns in Erlang, you end up with a system that should be scalable with some caveats of your own making. And clustering of Erlang is something that is much easier to do because Erlang supports clustering out of the box, at least in its basic form. So we knew eventually we were going to have a big cluster of these things. And because of the back-end systems we were talking to, machine A may pick up a message that is for a connection that lives on machine D. And we knew we had to solve that problem eventually. And in Erlang, that's much easier than what we probably would have had to do in Ruby or something else. So why Elixir and not Erlang? Especially at the time, Elixir was really new. I think we started looking at Elixir when it was at version 0.10. So it was a very early use of Elixir. The client had some existing experience with Erlang, but nobody on their team had written anything in Erlang. The people who had done that had left. They looked at some example Elixir code, said, hey, I can read this. I don't really know how to read the Erlang. And at the end of the day, we decided that, especially for a proof of concept, we could get this done faster and in a more understandable way using Elixir. And if Elixir as a language turned out to be a problem, we could always go back and rewrite it in Erlang. We're talking about probably 500 lines of code, at least in proof of concept, for this routing system that we had to build. So as a proof of concept, we picked up Elixir and kind of stuck with it throughout. For those of you not familiar with Erlang and Elixir, I want to talk really quickly about some things. A process in Erlang is not an operating system level process. Hundreds of thousands of processes on a single Erlang node are really common, and millions are not unheard of. You use processes to maintain state in a similar sort of way that you would an instance of an object in an object-oriented language in different techniques, but the same kind of idea. So you can use a process to maintain state. Processes talk to each other via mailboxes and messaging, messages are processed in order. OTP sitting on top of Erlang is the open Telecom platform, and it is useful for way more than Telecom. So if you look at that and go, oh, I'm not doing Telecom, I don't need to, you need to know about OTP. There may be some fringe case where you know about OTP and you decide specifically not to use it, but 99 times out of 100, OTP probably will help you solve your problem in a better way than you could come up with on your own. I am certainly not knowledgeable enough in Erlang to be able to say, oh, I don't want to use OTP for this. So OTP is kind of an abstraction on top of processes that gives you the ability to manage state and react to messages in a well-thought-out pattern. So you don't have to think about, okay, I've got this big loop of receive a message, and then how do I handle that message in this kind of larger chunk of code. OTP handles all those details for you, so you say, I want a process that is kind of a generic server, and it's going to do something. It provides a structure for your application. So OTP applications are generally large trees of supervisors that monitor other processes, some of which may be other supervisors, some of which may be workers. There is a saying in the Erlang community which is basically let it crash, right? So supervisors watch their children, and if one of them dies, they will restart it according to some rules that you set up when you start up the supervisor. And oftentimes, in the kinds of systems, especially that Ericsson was building when they were building Erlang, the answer is a retry is usually the right way to do this. And if you can reset your system to a known good state and then try again or continue from that point, a lot of times things just work. And then you look at the exceptional cases of, okay, I know exactly how to handle error X. I can write code to handle error X. But everything else, let's just try restarting the particular process that died, and 9 times out of 10 that'll work. And then you define some rules for what happens when it doesn't and things keep restarting. How does the tree react to that? How do supervisors react to that? And we'll get into more detail on that in a little bit. So I talked about supervisor trees. This application that we were writing is called Owsla, which is a warren. In Watership Down, the Owsla were kind of the police of the warren of rabbits. So that's where that name came from. So we have a top-level supervisor that watches some rabbit MQ communication processes, and then we have this tree of TCP/IP stuff that's going on. We have a TCP supervisor, and then the two ends of that are the listener, and how do I get new connections coming in, and then the endpoints, which are individual connections, and how do I handle those. So each one of those has a branch in this tree. So that's kind of like the really big picture. This is how our application is structured. You can see a couple numbers in there, like the TCP acceptor. There are 1,000 of those processes sitting there. We'll get into why 1,000 in a little bit. But it gives you an idea of the scale. So TCP endpoints, we were looking at 40 or 50,000 processes per node in our cluster, at least for proof of concept. So I'm going to talk a little bit about some of the things that we ran into as we were building this system, and what you can do about them. So I talked earlier about the fact that we were attempting to have a large number of devices, in this case thermostats, reconnect to our system all at once. So if you had to bring the system down, which you had to fairly frequently for code deploys on the Ruby side, when you brought it back up, they would all just come thundering back in, and then the system would grind to a halt, and things wouldn't connect, and then they'd come back 5 minutes later and try again. And there was this kind of long period before you got back to a stable system. One of the things that you have to deal with when you have a large number of TCP/IP connections coming in is how do you accept new connections? The canonical example that every language probably has somewhere is you create a listen socket, which is port 8080 or whatever your port is. You tell the operating system, I want to accept connections on that socket. And then you loop while you accept, which tells the operating system to block and wait for a new connection to come in. Once you get that accept return value, that's your file descriptor, your socket, whatever it is that your particular language abstracts that away to, and you hand that off to some other thread, some other process, something else, and then you go back to the top of that loop and start again. When you're talking about 1,000 new connections a second, that doesn't work really well anymore because you can't go through that loop fast enough, just accepting a new connection, handing it off, going back, accepting a new connection, and handing it off. So you end up building something called an acceptor pool. I had never really had to deal with something at this scale before. I did not know what an acceptor pool was, so we ended up building one. So why do we need one? We talked about, single-threaded listen accept doesn't really work very well, but it ends up that you can have multiple processes all calling accept on a single listen socket. And when a new connection comes in, only one of them will be woken up. And all the other ones are still sitting there waiting. So if you've got an 8-core machine, you can have 8 of them accepting new connections pretty much simultaneously. So the answer to this is have a bunch of acceptors all sitting there waiting on that listen socket. So we ended up doing this, and I'll walk through some code to show you what this looked like. The answer to the next question is, should you build your own? And the answer is probably no. I didn't know that we were building something called an acceptor pool when I started this. We built it, and then we kind of figured out, hey, we built an acceptor pool. This is kind of cool. And we posted something on Reddit, and somebody said, you just built Ranch, which is an Erlang library that is an acceptor pool. So everyone in this room now knows you do not have to build your own acceptor pool, at least if you're using Erlang. I'm sure most other languages have some form of this. So if you're doing Erlang, look at Ranch. If you're doing Elixir, there's Reagent, which is a pure Elixir acceptor pool. But the learnings were really interesting from that particular part of the project. So I'm going to walk real quick through some code. TCP Supervisor is not really very interesting. We talked about that tree where we've got the TCP Supervisor, and then we're just we have the listener side and the endpoint side. So this is an OTP supervisor written in Elixir. It has 2 children, and we're basically saying this is how we're going to set up the tree. When you call supervise, it tells OTP, these are the children that I need to start up. Please start them up for me. We'll get into a couple of different things about this strategy in a minute, but that's the basic idea, is you're defining your tree here. So if we go look at TCP listener supervisor, so my TCP supervisor starts up and says, hey, I need a listener supervisor. So this is the method that eventually, function. I'm an object-oriented programmer. I have to stop saying method when I'm talking about functional languages. So this is the function that gets called, this start link function gets called initially, and then OTP will eventually call this init function, which gets past our configuration that tells it like what port I'm supposed to use and things like that. The other thing is this acceptor count. So I said we had 1,000 processes sitting on that listen socket. We made that a tunable number. We set it to 1,000, and it worked fine. So for the proof of concept, we left it alone. As I said, processes in Erlang are very, very lightweight. A typical Java thread, I think, has a 2 megabyte memory footprint or something like that. And I think an Elixir or an Erlang process is somewhere in the 100 bytes for a new process. It's much, much smaller. So having a bunch of them sitting around is very low overhead. But we made it tunable just in case we needed to have more or fewer. And then we start up a whole bunch of TCP acceptors, but we don't do that here. This is just telling OTP, I am going to have some children of this type. And usually it just starts one up for you, but because we have this strategy thing here, so how am I going to deal with my children? And I'll get into some more details on that, but a simple one-for-one strategy says, basically, I'm going to start them up dynamically. So don't start any for me, just know that this is what shape they take. These are the parameters that are common to all of them and how I want to deal with restarts. And then I start up a whole bunch of them in this little enum.each, walk through my acceptor count and start up a bunch of acceptors that all listen on that same port. That one. So the endpoint supervisor is similar in that it's going to sit and just watch a whole bunch of TCP/IP endpoints. We'll get to this in a minute. Remember, that's important. We'll talk about restart strategies. But this does the same kind of thing. It just starts up a new TCP/IP endpoint. We assign it a UUID. so that we can communicate back and forth between the back-end processes, which are still written in Ruby, and this is basically a message router between TCP/IP and RabbitMQ. So when something comes back from the Ruby side, we know where to put it. And then we start up an endpoint. So that's kind of the quick overview tour of the TCP/IP stuff. I want to talk a little bit more about restarts. So this was a fun problem. So we're working on a proof of concept, and we have this testing tool that'll connect 5,000 new connections written in Go, interestingly enough, because we had something that was written in Go that basically did this already. So we want to test 40,000 simultaneous connections. We spin up another AWS instance, big giant box, and spin up a whole bunch of testing tools on it. And then we'd go through this system, and everything looks beautiful. We got 40,000 connections running. They're all routing their data back and forth. Everything is great. And then we go, oh, I want to tweak some parameters on my client. So I'd kill one of the 8 testing instances that were running, and the entire supervisor tree would just collapse in on itself, and everything would disconnect. We're like, I'm sure we've got a configuration problem somewhere. We'll figure that out later. So we walked through making sure all the other hard problems were solved. And then we came back to this and said, all right, so why is it that every time I disconnect one of these things, the entire tree just kind of implodes? No, it started back up, and you could start right up making new connections again. It's not like the system imploded. It's just we walked all the way back up that tree and shut everything down and restarted all of it. And this is when we get into a couple different things with OTP. The first one is restart strategies. Excuse me. So how do I as a supervisor restart my children if one of them dies? There are a couple of different ways you can do this. One for one, which is basically a child dies, I should restart that child. One for all is used if all of your children depend on each other. And if any single one of them dies, I need to restart all of them to make sure they're all in a known good state together. Rest for one is an interesting one. You saw in the supervisors that these, that's not a good example. Let's look at TCP supervisor. These things are a list, right? So there's an order to them. If you have multiple things that depend on A depends on B, B depends on C, C depends on D, you put them in the correct order in that list, and let's say C dies. Well, it'll restart C, and it'll restart D because it knows that D came after C. You know, so the fourth one came after the third one. I need to restart 3 and 4, but 1 and 2 are still okay. That's what rest for one is. And then this simple 1 for 1 is the same as 1 for 1, except the assumption is you're starting things dynamically, and that allows OTP to not track some state in the supervisor that otherwise it would as far as the order of starting things and stuff like that. So it's a little bit more efficient if you're dynamically starting a bunch of children. So that's number one, but that still didn't solve our problem. Number two is maximum restart frequency. There are 2 numbers that you can tweak in a supervisor to decide whether or not it should restart itself if its children are dying. Max T and max R are those 2 things. Max T is the time window in which it should be analyzing these things as a sliding window. And max R is the maximum number of child restarts that happen before the supervisor goes, wow, there's really something wrong. Maybe it's like my state that's the problem, so I need to restart myself. And those 2 numbers can be tweaked, but obviously we have 200,000 thermostats out in the wild, right? I don't want to restart my supervisor if 5 thermostats disconnect, because that's going to happen all the time. So you can't make that number really big in our case, because we don't want it to be really big. We want it to be infinity, right? We don't care. But that's not the right answer to that question either. The right answer is talking about child specifications. So I'm going to say this, then I'll show you the code. There are 3 different ways you can tell the supervisor to behave when its child dies. The first one is I should always restart the child if it dies. Doesn't matter Whether it said, hey, everything is great, but I'm stopping now, it'll restart it anyway. That's permanent. Transient is, it's okay if a child stops if it tells me I'm okay that I'm stopping. It terminates normally. And there are ways to indicate that when you stop a process. And the third one is temporary, which is what we cared about or what we wanted, which is never restart it. It's okay. So if you can imagine somebody's thermostat in their house, their Wi-Fi dies or their cable modem dies, well, their connection is lost. As a supervisor, I don't care. It'll come back in 5 minutes and reconnect. So I don't do anything strange. Just let those things die. And that's restart restart in the child specification. So if we look at, again, TCP endpoint supervisor. Excuse me. So this is the specification of what the children of the TCP endpoint supervisor are going to look like. And this was the thing that solved our, oh my God, the entire tree implodes on itself problem, right? So if you think about all the stuff I've talked about, the max T and max R settings, they both default to 5. So within a 5-second period, if 5 of your children die, you should restart yourself. We hadn't set anything other than the default values, so we would kill 5,000 connections in about 2 seconds, and the whole thing would just kill itself, right? So this is where you end up with this within the specification of the child telling the parent, how do I deal with restarts? And these guys are temporary. It's okay. We start them up. They live. They die. Don't do anything. And that was what solved our particular problem, but the journey of figuring out how to make this work correctly was walking through all of these different things, restart strategies, learning that what we really should be doing is simple one-for-one restart strategies, recognizing that max T and max R really aren't helpful for our particular situation, but they may be for somebody else's, and then finding the child specification restart stuff, which is what we really needed. And that is actually the talk in and of itself. So I have blown through this way faster than I have done in the past. So I have tons of time for questions. I can show you some other interesting things in the history of this code base. I can talk about some of the other stuff that we ran into with Erlang. And one good one is understanding the actor model and mailboxes. So if you saw right here, in fact, we assign a UUID to every connection that comes in. Well, I need some way to be able to find that process based on the UUID, because I get a message back from RabbitMQ that says, hey, I've got a message for this connection. Please send it to it, right? Here's the UUID. Do that. Well, again, not being experienced in OTP at the time we started this project, our first thought was, well, let's create a process that has a map from process ID, or from UUID to process ID, which sounds like a really great idea, except we're not running in a world where 72 different things can all access that one process at the same time, right? You have a mailbox. You have to send that process a message that says, hey, I've got this connection ID. Tell me what process ID is associated with it. So we built our own bottleneck, right? We now have a single process that holds all the state for every message route that has to happen. And we can only ask it one question at a time. That doesn't work very well. So it ends up that OTP has a solution to that, Erlang has a solution to that, and that's global naming. Endpoint supervisor. Where do we start this? Give me just a second. So there's our ID. Right, sorry. TCP endpoint. We want to look at the endpoint now. So to make our lives easier, we have a little structure that defines what the state of the endpoint is, and there's a bunch of stuff about handling messages in the proper order, because again, we've got a bunch of things listening on RabbitMQ, and a different machine may pick up our message and want to route it to us. The really important thing talking about dealing with these global names, there are a couple different ways you can name a process in Erlang. Either you just have a reference to its PID and then you can just call to it, or you can give it a name of some kind. There are local names which have to be atoms, and in Erlang, as with a lot of other languages, atoms are never garbage collected, so it's not a good idea to generate a bunch of new atoms and keep generating more atoms because you'll just run out of memory eventually. So that's not the right answer. However, global names take a binary, which you can create a binary out of a UUID. A binary is just binary data, right? So Erlang actually allows you to say, name this thing globally, which we needed for our clustering stuff anyway, because that means actually machine A can just say, I've got a message for something that's got this ID, please send it to it, and Erlang will figure out where in the cluster that thing lives and send the message to it automatically. So this was pretty much all of the code we needed to write, A, to handle that mapping in a way that wasn't bottlenecking the entire system, and B, to allow us to route messages to the right connection, right? Which machine is this thing living on in the cluster? So this gives it a global name with that ID, and then the send, which again gets picked up, the RabbitMQ listener calls send, says it's got a global name with this connection ID, and routes it to the right place. Yes? Yes. Yes. Yes, yeah, and we started looking at using ETS tables for it, and at the same time figured out that global naming existed, and decided that seemed to be a reasonable solution to the problem. You're right, and in a lot of cases that's not a good answer, and essentially intellectually sharding across a number of processes is the right answer. So he mentioned two other ways that we could deal with this. Right, we're talking about a UUID as a series of bytes. And you could shard across a whole bunch of processes using the first byte as a key, right? So I can have 256 processes, each one of which has a submap of all of the process IDs. And I get a connection ID, I pick the first byte, I go, oh, I need to send it to that one to get my map back. As I said, we kind of figured out ETS tables and global naming at the same time and went with global naming, but it's not always a good answer, and for those kinds of problems where you found yourself in a bottleneck, that's often the right answer if you're not talking about finding a process, right? This was a very special case where there was a different answer to the problem, but if you need to find ways to shard your information, your state across a bunch of processes, that's another good answer for how to do it. The third one is ETS tables. So Erlang will let you store data out of process in a table somewhere called an ETS table, and then go back and get it by key. It's a pretty simple key value store, but it's enough that we could have solved this problem that way as well, right? Every time I create a new connection, I put it into an ETS table with the process ID and the key, and the connection ID as the key, and then as I come back, I can just go look up the process ID in the ETS table. The downside to that for us was when we went to a clustered solution with RabbitMQ, we could have a single machine pick up the message and then use global naming to route it to the right place. Whereas if we had stored things in ETS tables, not distributed across all the clusters, all of the different machines would have to pick up that same RabbitMQ message, which RabbitMQ supports, but it takes more network overhead. And then the one that has the connection could have gone, oh, I got it, send it off, and everybody else could have just ignored it. And then there's amnesia, which is distributed. Anyway, you can get into another layer down where you've got some distributed shared data that you can use with amnesia. But as I said, for us, it seemed the right answer was using global naming in this particular case. So we have about 11 minutes. I am happy to entertain questions. Yeah. We actually, yes, absolutely. So the question was, we probably had some pretty robust logging in order to, don't go to sleep on me. There we go. We probably had some pretty robust logging in there. Honestly, for the most part, we did a lot of this with small bits of logging where we were finding problems, and then removing it when we didn't need it. But once we got past the proof of concept stage, we actually put Logger, L-A-G-G-E-R, which is an Erlang library for doing logging, into the system and started to instrument it, because you don't want to, I mean, this is all at the proof of concept was successful point in the code. It got more complicated after this. But for demo purposes, it's a lot easier to look at this and say, oh, this is how this all worked. But we did start to instrument a lot of those things. And the key is to be able to understand, things like log levels and what do you care about when, and, ignoring the things you don't when you're in production. And I think that's probably true of any programming language, right? Most logging systems let you turn on and off certain levels. And so when you're in a diagnostic mode, when you're really running into problems, you can crank up logging. The guys from Riot Games were talking about being able to enable and disable logging for a particular user at different levels, which is a really neat idea, right? I know that a particular user is having a particular problem. I can just go in to a live shell in Erlang and turn on additional logging for that user and not overwhelm the system just with logging data, but get more information on that particular user to be able to understand where the problem lies.
Was there any point where in the project where you ran into limitations or abstractions that Elixir made over Erlang where you might need to rewrite this in Erlang?
No. So the question was, did we ever run into issues where Elixir had put an abstraction on top of Erlang that prevented us from doing something we needed to do, and did we have to drop down to Erlang in order to do those things? And for this system, no. And I've never heard of anybody who's really run into, I can do something in Erlang that I can't do in Elixir. The more I used Elixir, you'll learn you have to at least be able to read Erlang, because so much of the documentation and so many of the open source libraries that you're going to want to use are written in Erlang. And anything you can, any library that's an Erlang library, you can call from Elixir. So there's pretty much total transparency between the two languages as far as being able to call out to Erlang libraries and things like that. And in fact, a lot of the stuff that we used were base Erlang and OTP libraries. The SSL library that we use, the socket stuff that we're using is all straight out of OTP and Erlang. There are now wrappers around a lot of those things, or as I said, there's like an Acceptor Pool implementation that's written in pure Elixir. At the time, most of those things were either just barely forming or weren't there, but we didn't have any problems because we could just look at, learn use some Erlang, and figure out how to do a lot of this stuff and use Erlang or call into Erlang where we needed to. But no, we never found anything in Elixir that was like, oh wow, I really can't do what I want to do, and I know I can do it in Erlang, so I'm going to have to go write this particular module in Erlang or anything like that. Yes?
I was curious, what language features you used from Elixir? Did you use macros?
So the question was, what language features did we use from Elixir? I will tell you that in the example code that we looked through, it's pretty straightforward. You could have written all of this in Erlang, and there was nothing really that was different. There are, however, some libraries that we're using that we have either modified or are in the middle of modifying to submit patches to. There's one in particular. At one point, because of a deficiency on the Ruby side, we had to punt on RabbitMQ and build something in Redis to do the one way of the messaging without getting into details. But that meant we needed a Redis client. And there is one. There's an Erlang Redis client, and there's even an Elixir wrapper around it. But I don't know if you've ever seen if you've ever used Redis. There are, I don't know, what, 150 or 200 operations that you can call on a Redis server to do things. I'm in the middle right now of rewriting that Redis client, which literally defined each one of those by hand and only had about 20 of them. So every time we needed something that wasn't there yet, we had to add it, and then we'd submit pull requests and stuff like that. Interestingly enough, the Redis people build their documentation from a JSON file that describes every operation and its parameters. So I'm in the process of writing a macro that takes that JSON file and literally creates the Redis client, including every available operation on Redis, just by reading the JSON data. So there are some really interesting things you can do with macros in Elixir that really didn't come through in this particular talk, and unfortunately I'm not quite done with that code. But those kinds of things are pretty common in Elixir. Yes?
So kind of related to the earlier question about logging, does Erlang give you much in the way of metrics to see things like user processes and how the goes?
Right. So yes. So the question is, does Erlang give you insight into performance metrics within the Erlang VM itself, right? Like mailbox steps and things like that. There are an awful lot of libraries that provide some very detailed and interesting live metrics or reported metrics out of Erlang. And yes, you can see lots of those things. Unfortunately, in this project, I was working as a consultant for another company and the contract ended, so that was kind of the end of my work on this project. We didn't get to that point of operationalizing the system, but yeah, you would definitely want to and would be able to fairly easily monitor those kinds of things. Somebody recently, like very recently, just put out a little PDF book about running Erlang systems and the kinds of things. And I'm sorry, I can't remember the name off the top of my head of the book. I'll try and find it and tweet it after the talk here. But they talk a lot about monitoring and logging libraries and what you can do with them. So it's a really good resource. In the back? Erlang and Anger. Thank you very much. Yes, that's the name of the book. And it's like 97 pages, and I devoured it on my way here, actually. I think it came out the day I was traveling. So a really nice collection of lessons learned from their experiences running Erlang systems. Yes? So the question was, Elixir is a dynamically typed language. Does the compiler give you any feedback on typing or things like that? And the answer is both Elixir and Erlang are dynamically typed, but they also support speccing your functions. And there's a tool called Dialyzer that you can run on your application, assuming the libraries you're using are specced, and it will warn you about potential violations of the specs. So that's definitely a good tool to look at if you want to get some of the safety features of a statically typed language while using Erlang. Speccing your functions and using Dialyzer is the way to do that. Any other questions? Yes? I'm sorry, can you speak up just a little bit? Okay, so the question was, why did we use HTTP versus something like XMPP as a protocol? So first of all, if it wasn't clear, we weren't using HTTP. We were using TCP, but the protocol was not HTTP. That being said, the protocol that they used was a custom text-based protocol that was very verbose and not real efficient. And one of the things they ended up doing fairly far along in the project as they're building these thermostats is they moved to protobuf as a protocol for transferring data because the text-based protocol was just really verbose. and was just unnecessarily verbose and also complicated. So it wasn't verbose and human readable, it was verbose and ugly. So it didn't provide any really useful things, so they moved to protobuf for that. Okay, thank you all very much. It is time.